In this video, we will talk about the numerical method for diffusion equation. We already saw that what is the advection equation, linear form, and the nonlinear form. For example, if we have a general form of conservative form for first order method, if I replace flux with u bar q, then we get partial q by partial t plus u bar partial q by partial x is equal to 0. This was the advection equation. If I replace this flux with q square by 2, then we have partial q by partial t partial by partial x, q square by 2 is equal to 0, and this becomes partial q by partial t, q partial q by partial x is equal to 0. So this is Inviscid-Burger's equation. So it means that if we keep changing this flux, then we can also get the second order differential equation. So if I replace this flux F with minus beta partial q by partial x. On the left hand side, previously this f was a function of q and t. Now f is a function of the derivative of q with respect to x, and it is a function of t. So we can put this value over here, So we get partial q by partial t plus partial by partial x minus beta partial q by partial x is equal to 0. And then we have partial q by partial t is equal to partial by partial x beta partial q by partial x. Here beta can be a constant, it can be a constant, it is diffusivity. It can be a function of x and t, maybe. It can be a variable, I should say. So we want to find the numerical scheme that can solve this equation. Okay. We just follow the same procedure as we did earlier, which was like this: qn plus 1i is equal to qni minus or plus, it should be minus delta t by delta x, and then we have f n I plus 1 half minus f n I minus 1 half, and we know that we have to put the value from the neighbors. So we introduced some function which give us the value for these fluxes, and that was flux for Fn, maybe something like that, Qn I plus 1 minus F Qn I minus 1 Qni. So this is our numerical scheme, Qn plus 1 I. Okay. So we want to put the over this flux over here. So we replace this flux for over this scheme. So we write F, the flux Qn I minus 1 Qni is equal to minus beta, since we are putting the value for I minus 1 half over here and from this over here, and beta is a variable, so we can keep this as beta I minus 1 half. And since this Q is approximated with Qn, depends where we are, with Qn some quantity, and there is a gradient as well, so we can approximate this with Qn I minus Qn I minus 1 divided by delta x. Similarly, we can also replace this quantity with some another formula, which is F Qni plus 1, that will be minus beta. It is at I plus 1 half, and the gradient term will be equal to, uh, let me just see that. For example, if we have I plus 1 half, and this is I minus 1 half, I minus 1 half is computed from Qni and Qni minus 1. So if we have I plus 1 half and we have I plus 1, so it can be computed from Qni plus 1 minus Qni divided by delta x. That's how we compute flux for the diffusion problem. Okay, this is our diffusion problem. Remember that diffusion means we have a second derivative for x. Okay, so we can write this as Qn plus 1 Qn plus 1 I is equal to Qni plus delta t by, we put the value of these fluxes over here, delta t by delta x whole square. First we put the value of beta I plus 1. Since it is negative, so we take negative as a common and we solve it. So we get beta I plus 1 half Qn I plus 1 minus Qni minus beta I minus 1 half Qni minus Qni minus 1, so on. So this will be our formula for the diffusion problem. If we want to keep this beta as a constant, if this beta is constant, then we can write Q n plus 1 I is equal to Qni plus delta t by delta x whole square. Beta will come outside from the brackets since it is just a constant, and then we have Qni plus 1 minus 2Qni plus Qni minus 1. So that will be equal to beta delta t by delta x square. So this is our formula for the diffusion equation. And remember that our diffusion equation was partial q by partial t is equal to beta if beta is constant, partial square q by partial x square. This was the diffusion problem. You have seen probably the similar thing for the heat equation. This is heat equation, beta partial square t by partial x square, and at that time we have alpha over there. Okay, so we have solved, not solved maybe, but we have developed the formula for the diffusion equation. In finite difference method, you probably have seen such formula over there when you solve the heat equation. For example, if we have heat equation alpha partial square t by partial x square, for the time we have Tn plus 1 I minus Tn I divided by delta T is equal to alpha Tn I plus 1 minus 2 Ni plus Tn I minus 1 divided by delta x whole square. So when we solve this equation for Tn plus 1, the solution at n plus 1th level, we have Tni plus alpha delta t by delta x whole square, Tni plus 1 minus 2Ni plus Tni minus 1. So this is from the finite difference method, and we can see that this formula and the formula from finite difference method is same, but the construction for this method is different. We constructed this over the finite volume method. Thank you for watching.